Okay, this is our second video regarding the fixed point iteration. What I will show you, a new function. This is a function f1, okay. X equal f1 equal 1 over 50 x equal cube plus 4 over 3 minus 2 over x squared plus 2. Now we'll try to find out if we can find how many points, how many solutions for this function. Some of the solutions will be able to determine, the others we need to change or modify the function one in the way just same as I showed you in the first video. So that's number one, that's the original function f1. So f1 here is the original function, and then if we want to modify it, we multiply both sides by -1, so we get minus x equal minus f1. Then we add 2x to both sides, so obtaining x equal function 2. So some of the points that we could not obtain from the original function will be able to obtain from the modified function f2. But sometimes even the modified function may not help us. In that case, we need again to do further modification. So that's step 3. We add to both sides r naught x, where r naught any positive figure. It could be 1, 2, 1 point something, okay. We add it to both sides. Then we obtain x by multiplying f2 plus r naught times 1 over r naught. So I'll show you how we do that, okay. Now I have already typed program. I sent it to you today through the WASC group. I want you to edit it yourself in MATLAB and experiment it, okay? But I'll show you how you do that. So this is the fixed point iteration, okay? Fixed point iteration. Original function is f1, okay. So x should be f1, and what we do, we try to define a vector x, the value x from -10, 0.01 step up to 10, and we say y equal x, that's the linear line. Then what I did, I defined an index, we called it fixed. If fixed equal 1, then we use the original function. If fixed equal 2, we use the second function, which is multiplied by -1 both sides. And if the method or the index is fixed equal to 3, then we add r naught x to both sides, okay. So let's go to the first one, and okay. So what we want to draw the function, so if fixed equal, we define function 1. As I told you in the previous video number 1, so what we defined here is the starting value. We called it p naught, okay? And then we obtain for that value, we obtain what is function 1 for that value. So that's why we put it 1 and 1 here, okay? Then plus 2, okay, that's no problem. And then we do the iteration from 2 to 20. You can go more than 20 or less than 20. That's depends on the significance or the error. If you achieve within a tolerance, a good tolerance within 20. If you want to reduce that tolerance, then you can go, say, 25 or 30. Okay, you can experience that. Then after we do that, so what we are creating a vector, that's the iterations xx and ff, depending on f1. Okay, then what we do, define another vector x naught f naught. We define two values first, the same x naught, okay, and then x and f, and then we modify them. Don't forget to enter here k, not 1 in there. So we update that vector, and then we can plot it. Okay. Given that whole plot here, x and y, and then x and function 1, and the iterations we start with the fixed point iteration x naught and f naught, and then you can here describe the line width, so it will change the font of the line width. I put it to here, I can make it 4, that would be more even. Okay, and let's select a starting point and see what will happen. Okay, we'll come back to here. Okay, let's first define our index, which is fixed, and make it equal 1. Okay, so our index fixed is equal to 1, which means that we want to test the original function. Okay, let's also give p naught a value, say equal, for example, we start at 0. Okay, doesn't matter, p naught is 0. Then we do the fixed point iteration. Undefined variable fixed point, because you know why? Because I did not, I should set the path. Okay, you may face this problem, so you go to home here. Okay, and set path here. Okay, set path, add folder, because I have it in desktop. I made this folder for it, and I put it there in J. Okay, so select folder. Okay, and that's it. Okay, so let's try it again. Fixed point. Okay, it's doing it. Now it will plot it. Okay, if we see this, let me enlarge it rather. Okay, this is our function, original function, and this is y equal x, the linear function. As you see, the linear function intersects with the original function in 3 points. 1, 2, 3. We started at 0, and it proceeded and it's found for us the first solution. It converts. If you start anywhere here in this region, it will convert to that. If you start in this region, also it will convert to this. If we start in this region, it will diverge. It will start in this region, also it will diverge. Okay, so only this point will be able to obtain from the original function. So we started at 0. Let's start at another point. Change p naught, say to -6, for example. Okay, -6 p naught. Let's make it -6, and do again the fixed point iteration. You see, we started at -6 here. When we choose the vector, I showed you that x naught equal x1 and then x1 means that is x. This is the first point, the same x, and this is second point x. So the first point we have selected f naught on the linear curve, and we find what is f on the original graph. So it will move like this. If you can sketch an arrow, try to find out if you can make an arrow here, okay, with the sketch. I didn't have the time to do that, but I think you'll be able to manage. So it converts to this point here. Let's see what is this point here. If you look at x naught, that's the vector. So it's the same for f naught also. Okay, to reach. You can plot this if you like. If not, you can plot it and see. We started at -6, but it moves and it converts to point something. That's 0.4135. That's the final value. So we succeed to find out that value, because we know that if we do it again, okay, fixed point, you see in here, because the slope here of the function is less than 1, the absolute value is less than 1, then this point is stable. If you start this side or this side, it will convert to this point. However, this point is not stable because the slope is greater. You remember, this is y equal x. So the slope of this line is equal 1. So the slope at this point here of the curve is greater than 1. Similarly here, the slope is greater than 1. So that's why it diverges. This point is not stable, this point is not stable, while this point is stable. Now let's start somewhere, say 6 near that point. But you will see that it will convert to this point, it will not go there. Okay? Let's start at 6. P naught equal 6, and do the same procedure. Okay, you see here. So we started at 6. It didn't go there. It comes like this here. Okay, like this, and then finally it converts to here. Okay. And we can plot it if you like, if you want to see it, okay? So that's so it again converts to the final value, okay? And you can check this, the tolerance, if not end minus x naught end, it will give you the tolerance, which is 10 to the minus 7, which is fair enough, it's good. Okay, let's now, let's see. Okay, what we want to do now, let's start from at a point at -8 and see where it will go, because this side we expect that it will diverge, and at a point greater than this, let's say 7, it will diverge. Will 7 or -8 should diverge? Okay, let's do it. -8, start -8. Okay, here -8, -8, and see what happens. Fixed point. Okay, you see, because it has gone to very large value. See, 10 to the power 189. So if you look at this one, if not, you see, infinity minus infinity. Similarly, x naught, okay, it's minus infinity. So we want to draw that and see what happens. So let's say plot the same what we have there. We remember it's f1, yeah. It's not f2, f1. Never mind. So that's f1, okay. So we are plotting plot x and y, x and f1 and x naught. Let's go just to 1 to 5, okay? Only 5 iterations and see what happens. You see, if we can, you can look at that. We started here, so it didn't go that side. It comes the other side here, so it's diverging, okay? And similarly, if we start at a point, let's say 6, let's say 7, somewhere here, 7 maybe, again it will diverge. to that to the part M. Okay, let's try the 7 and see what happens. Okay, fixed point. Okay, again, it's similar to the other problems here. So we'll just plot 1 to 5 and 1 to 5 and see what we get. Plot. Okay, we are here now. We started at 7, so it jumps to this point, then goes to this point, jumps, and it will divert. It will not go to the solution. Okay, which means that we need to modify this curve, original curve, so we can find out the solution at this point and at this point here. Okay, so that's what we will do now. We'll modify this f1 to function 2, and we'll start also the same way. Okay, so let's change the fixed index. Instead of 1, we make it 2. Okay, we make it 2, and now run the program again. Okay, so you see this has changed. Okay, this function, when we multiply it by minus and add to x to it, it's changed to function 2. So this is function 2 now. At this point, which was stable, here this point was stable, now it's unstable. We'll not be able to find the solution at this point here. But we found the solution from f1, so it doesn't matter. What we need is this solution and this solution. Okay, this solution, if we start anywhere in this range, we started at 7, so it came back to this one, this point here, and this point, so it converted to the solution. So we had no problem at this one here. We managed to find a solution at this unstable point. Now this point here became stable. Okay, so let's look at the plot if not. As you see, we started at 7. It comes to something like 5.8 something, and then oscillates, and finally it finds the solution. Okay, so that's an oscillator solution, but it converts to the final solution. So we have 6 point something the final solution. It's probably 6.3, and we can check that. Okay, if not 6.3 something. Okay, and you can find out what is the value by finding what is if not end the final value. Okay, 6.31 approximately. Okay, now let's run it again. Just to okay. Now we started at that side. We can start at a point nearly, let's say 9, and see what happens. What I expect, if we start at 9 here, it will come to this point here and then again convert to that point. So let's start at 9. P naught, okay, equal instead 7 or 7, let's say 9. Okay, and run the program again. You see, and here we started at 9, so it comes to the function, which is function 2. Then it goes to the line horizontally, then moves vertical, horizontal, vertical, horizontal, vertical, until it reaches this point. So again, as long as if we start this value here, you see, if we start somewhere at this value, it will come to this point here. Okay, so if it comes this point, it will try to go to this point here. Let's start something like this, even at 10. Okay, let's see at 10. At 10, it will not convert. Okay, let's start at a value 10 and see what happens. Okay, fixed point. You see the problem here? We started at this point here, 10. Now, it moves horizontal, but it will reach this region. It's not this region. For convergence to be achieved, we must, for this point, we must reach this region. Then it will converge. If we reach this region, it will not go to that side. It will come to the other side. But as you see, it does not converge to this point. It keeps oscillating at this point. Why? Because at this point here, the slope is high, higher than 1. It's negative, but the absolute value is more than 1. While the slope here, you see, this is the slope, is the absolute value, it's negative, but the absolute value is less than 1, so that's why we were able to find the solution here. So we have a problem still here. We have to modify this function again. But let's, before doing that, let's see the graph over. Plot, if not. And you see, we started at 10. So it tries to convert to a solution somewhere here, but it will not be able because it will be oscillatory. You see, that's the problem. Okay? Let's do it again and see where we are. Anywhere we start this point, so even if we start at 0 here, it will come 0. Anywhere we start in this region here, okay, it will keep oscillating as pi. Let's start at -2 and see what happens. P naught. Even at 0, I expect that you will not get a solution. Okay, fixed point. Even at 0, you see, anywhere we start in this region, it will go and keep oscillating around this point here. And we can see that plot, if not, we started at 0, but it goes and oscillates to an. So expect that the value of the solution here is negative, but it keeps oscillating around that solution. Which suggests that we need to modify the function to be able to find this solution somewhere around probably -7. Okay, let's do it again. And here, so the solution we see is negative, but less than -8, between -7 and -8. If we start this side, say at -10, for example, it will do the same problem. Okay, let's say -10, okay, and do it the same way. You see, again it will move vertically to the function, then horizontally to the line, and then vertically to the function, horizontally to the line, vertical, horizontal, and so on. So again, it keeps oscillating around this point here. And let's see how plot this. Okay, so it comes from -10, but it keeps oscillating around this point. So it suggests that we must modify that function. Okay, to modify that function, what we need to do is to go to the fixed and change it to 3. The index, we change it to 3 because we go to function number 3 or function 3. Fixed, we change it to 3. Okay, so we change that to 3. Right? Now, before doing that, we must define R0. Let's give R0 1. R0 equal 1, for example. Okay, and see what happens. Fixed point. Okay. Look at the function. This is function of 3. Okay. Now the slope, okay, has been reduced. It is less than -1. Less absolute value. Now this point became stable. Before it was not stable. Now it became stable. This point is still stable. This point is not stable, but we found out that point from function 1. So it doesn't bother us. What is the problem was this one. So we were able to find, to scale or modify the function to f3 and made this point stable. Let's go back to the program and see. The program now, if x is equal to 3, so it comes to here. And you remember, this is not. This for registration. We added r naught x plus r. We added r naught times x to both sides. R naught here, I'll just, you modify it here, r naught times x, just a demonstration. You can correct that in your note, okay? Then it's correct here. Then we take that x a common factor, so it will be 1 plus r naught. We divide both sides by 1 plus r naught, so obtain f3. That's what we did. R naught, we made it 1. If you are not successful, then you make it probably 2, 3, and so on, until you achieve a suitable function, okay? So let's go back to our program. Okay, we were able to find a solution, and let's look at the solution, at the iterations, the plot. Okay, this one here. So we started at -10. It jumps to negative and then back and keeps. Okay, it's stable now. It's -7 point something. Okay, we can find out that value from f naught and -7.6485394. And if you want to test the tolerance, okay, that's the tolerance. It is 10 to the -11, which we are very happy about that. Okay, let's start at another point. Okay, anywhere we start below this point here, it will converge. Anywhere start in here also, it will converge. Let's start at -2 and see what happens. P naught is equal -2. Okay, fixed point. You see, again, it will converge. We started at -2, vertical, horizontal, and it will reach that solution. Okay, if we start at this point here, it will go to that solution. If we start at this point here, it will come back. So all the 3 points now, this point and this point, are stable. This point is unstable. But if we want to find the solution of this point, we should use the original function. Okay. Do you want us? Okay, let's look at the convergence. Okay, so that's the convergence characteristic. Okay, we can obtain now. We know f1, we know f2, we know f3. Let's plot them and see how do they. Okay, this is f1. Just okay. XY is the same. Let's just copy this one. Okay. Delete. Insert. Okay. So the y, the linear, is black. K is black. F1 is red. Let's make this F2. The second function, let's make it say blue, and P3, and let's make it green, G. I think green is G. Okay, we remove this one, it's an extra. Okay, and let's see what's in there. What is this? Oh, we forgot something here. There's a mistake here. Yes, you're right. Okay, comma here. Another comma somewhere probably. Yes. There is in here. We forget that. Okay. Yeah. Look at this three functions. Okay. You can draw them. Practice that. You remember the red one was, this is the linear, y equal x, the black color. The red color is the original function f1. Okay, we see from the original function this point is stable here. This point here near zero is stable, this point here. Okay, but from the original function, the red one, the slope here is greater than 1, positive, and here also greater than 1 positive. So that's why from the original function, this point here and this point here were not stable. Now, if we go to the blue one is function f2. So this point became stable, but this point is still unstable. Why? Because the slope here is greater than 1 absolute value. When we modify it to function 3, we reduce, you see, we reduce the slopes here. We reduce also the slope here. But this point here, it was stable and is still more stable now. This point here was not stable. Now we reduced the slope and it became stable. Okay? What I want you to do is to practice now. I sent this to you through the group, the WhatsApp group. I sent this to you. I want you to type it in MATLAB, your computer MATLAB, and practice it. Okay, practice and understand why we do this. Why we do this here, okay? And once you digest everything and understand everything, try another function yourself. Try function 1 and modify it, okay? Yourself, add for example, to it a sign, or add to it an exponential, okay? A square root, and practice it, okay? You will, I'm so sure that you will understand it very well, okay? And you can use the line width here to change this either to 4 or to 2. 1 is no good, 2 reasonable, 4 it's okay. Let's see how it looks like. Here it's 4, okay? No. There's a problem or what? Okay, plot. Yes. Yes, here it is. Okay. This one is font size is 4, okay? The line width is 4. Let's go to 2. Let's see how it looks like. This 2. Yeah. So it's thinner, right? Let's go to 6. Or 8. See? It's too large. Okay, you can okay. For the sake of demonstration, you can practice these things. Okay. So I want you to type this one yourself and try this program. Understand it first. Try it and apply it to different functions. Okay. So what I will do now, I'm planning now to upload this video and send it, inshallah, tonight. I'll send it to you through the group, and I will send it through the Blackboard also, to the Blackboard. Video one now I already sent last night, and I uploaded that video number one also to the Blackboard. Okay, you are there, all you can see it, you can watch it there. So I will upload the video to this one here, and to you through YouTube, and from YouTube I will send you the link, okay, and also the link I will send it to the Blackboard. Next week, inshallah, what I will do, I'll try to go to the triangular factorization. I'll find I will find out the topics that might be a bit difficult to be understood from the notes. So I'll make a video for those topics that it needs further demonstration, but you read the notes, and I think the triangular factorization, we need a video for that. And then we'll move also to curve fitting and these things, okay? So I will be in touch with you mostly this way, video and MATLAB, okay? And I will send you through the Blackboard. I will send you also some quizzes. I want you to practice, solve it, send it back to me, and the assignments, work on them. Send them to me also through the, I think there's a procedure, you learn, you know that better than me, through the Blackboard. And after I see that you had enough knowledge, okay, what I will plan, sort of video interviews with you, with each of you. Every day, say 3, 4, 5 students. I will interview you through the video. We should learn how to do that through probably the server of the university. So a sort of a test. I will test everybody, okay? A verbal test. We talk through the video, ask you things, and see how you knowledge. I think this semester we should follow these interviews to assist the students. Okay. Anything you can send your note, any note you send it through the discussion and the I don't know, probably I have to open sorry, a discussion file through the Blackboard, and also we can communicate through the WhatsApp application. Okay. I'll try my best, okay, so that you understand the material nicely, okay. Unfortunately, that's what happened. So just keep safe, okay. Keep out from crowding with people, okay. Keep at home. Study fine, and let's communicate together, and inshallah I ask God that we pass this trouble, inshallah, as soon as possible. And you pray for God also with me, and all we pray for the sake of humanity everywhere, and inshallah it will pass, okay. So I'll talk to you later when I prepare another video. I'll choose a topic and prepare another video. Okay? So talk to you later.